And this carbon chemistry is one of the most important chemical couplings that link chemical reactions with climate. And we look in particular at acid-base reactions, the subject of Chapter 6 in this course. But we look at the distinction between what happens when carbon comes into contact with water, both fresh water and ocean water, and how important that is for life systems on the Earth and in the oceans. And probably the most important example involves ocean chemistry of carbon. So if we take a healthy example of fish life in the oceans and the way it interacts with coral, we find that at 375 parts per million of CO2 in the atmosphere, the life on the coral reef is extremely healthy. And corals are very interesting because they're actually animals. They are symbiotically related to their surroundings, but they're also extremely sensitive to those surroundings. If we change the temperature of water just by 2 degrees Celsius from current temperature, and we raise CO2 to 450 parts per million, it turns out that the coral reef essentially dies, large parts of it. And this is happening to coral reefs worldwide. If we go to plus 3 degrees Celsius and increase to 500 parts per million of CO2 in the atmosphere, these coral reefs are essentially dead. And when they die, they cannot be regrown. Now, 500 parts per million of CO2, we're currently at 400 parts per million. But if we continue burning fossil fuels at the rate we are currently burning them, by the end of this century, we'll be at 900 parts per million of CO2. So you can see the carbon chemistry of the oceans turns out to be a primary and essential constraint on the amount of carbon dioxide that can reside in the atmosphere. So let's take a look at that. Let's examine this beaker. This is a beaker of water. In this case, we'll start with fresh water. And we can contrast nitrogen with carbon dioxide because nitrogen in its gas phase can be included into water, but it's a physical binding of the N2 molecule into the interstitial structure of water. Carbon dioxide is a very different story because carbon dioxide in the gas phase goes into the aqueous phase, but that carbon dioxide in the aqueous phase is converted to carbonic acid, H2CO3. Well, if that was the end of the story, it would be one thing, but what happens to that molecule of carbonic acid? That's the next question. That's when the story becomes particularly interesting because carbonic acid, being an acid, releases a proton, H+, and the bicarb anion, HCO3-. And as we know from the chapter, there's an equilibrium constant associated with that, and that equilibrium constant is 4.5 times 10 to the minus 7 moles per liter. But that bicarb anion also dissociates in water to form another proton, contributing again to the acidity. But that second dissociation constant is 4.7 times 10 to the minus 11 moles per liter. So if we're talking about fresh water, it's that first dissociation constant that determines the acidity of fresh water. And as we'll see in a little bit, that acidity of fresh water turns out to be very important for the history of climate, because when a raindrop falls through an atmosphere containing CO2, it comes into equilibrium with that water droplet, forming carbonic acid that then dissociates to form the bicarb ion in that little raindrop. And that acidity in rain, when it interacts with the crust of the Earth, turns out to be the dominant factor controlling climate over periods of millions of years. Now, the interesting thing about seawater is that it contains many positive and negative ions, and it turns out that the most important factor in determining the positive ion contribution, the acidity of water, turns out to be the balance between those positive and negative ions. And in seawater, the pH is determined by that charge balance, and the pH of seawater is about 8.2. So it's basic in its character. And at a pH of 8.2, it's the bicarb anion that dominates the concentration of the inorganic carbon constituents in seawater. It's also interesting, isn't it, that the pH of seawater is very close to the pH of blood of organisms, and there's a reason for that, and it's related to the origin of species in the ocean system itself.